Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to cover even and odd identities for trigonometric functions. You should have just finished watching my video on the Pythagorean identities. Up to this point, you should be very familiar with radian measure, reference angles, arc lengths, special triangles, right triangle trigonometry, unit circle trigonometry, trigonometry with any size circle, the cofunction identities, and finally the Pythagorean identities from the last video. And now we're going to tackle the even and odd identities. And this will round out, I should say, all of the fundamental identities for trigonometric functions. There are a ton of other identities. If you haven't had trig, you don't know it, but there are quite a few other identities. But for right now, this will round out all the basic identities we need to go into graphing trigonometric functions. So let's state it right here. The sine, the cosecant, the tangent, and the cotangent are all odd functions, while the cosine and secant are even functions. Now, before we begin the proof, I want to remind you that an odd function has the property that f of negative x is the same as negative f of x. And that's actually how you prove a function is odd. You start with f of negative x, you work your magic, and then hopefully it comes out as the opposite of the function had you not plugged in the negative for the x, and that would prove it's an odd function. Even functions, on the other hand, have the property that if you evaluate f at negative x, it'll just return f of x. So the negative as the argument will disappear. So let's go ahead. Oh, and by the way, also, graphically, a function, if it is odd, it is symmetric about the origin, and graphically, if a function is even, it's symmetric about the y-axis. So those should be strongly familiar to you. And now we'll start into the proof, which requires me to actually draw. There we go. We have our circle. Let's just call this a unit circle, because it doesn't actually, the proof doesn't change if it's a non-unit circle or a unit circle. So we'll go ahead and assume we have an odd function, or sorry, not odd function, but a unit circle. All right, let's also consider t to be the arc length along the unit circle, the circumference of the unit circle, from 1, 0 up to some point x, y. So I'll just go ahead and highlight out some arc length here all the way until I get to a point, which I shall call x, y. By the way, we know by the unit circle definition that is actually not just x, but the cosine of t if that arc length there is t. So I'll write it in that way. It's just a unique way to see it. X is cosine of t, and y is sine of t. There we go. It's just kind of an interesting way of thinking about it. And now what we're going to do with these functions is we're going to plug in to cosine, sine, tangent, cotangent, all that fun stuff. We're going to plug in the opposite of t and see what happens. So over here, I'll just start writing those out. And we're going to investigate what happens with those. So let's see. Here is t right here. If we want to go negative t, instead of positive t, we would have carved out this arc length right here, but it would be the same arc length otherwise. So it would cover the same distance, just in the negative direction. So that point right there would not be necessarily cosine of t, sine of t. And in fact, it's the cosine of negative t, right? Because that's the distance we've covered there. And the sine of, again, negative t. Well, let's take a look. The cosine is the x value. The question here is there any difference between the x value at this point and the x value at the point down there? The reality is there's no difference between those two x values. So that is the cosine of t is actually the same thing as the cosine of the opposite of t, at least in this picture, and that's good enough for me. So the cosine of the opposite of t is actually the same as the cosine of t. If you look at the sine, well, these y values are not the same, right? This y value is some y value. I have no idea what it is. This, due to symmetry, is just the opposite of that y value. So if the sine of t is y, the sine of negative t is the opposite of y. Let me write that in here temporarily. It's the opposite of y if sine of t is equal to y. Oh wait, what did I just say? Sine of t is equal to y? Okay, well if sine of t is equal to y, then I'll just replace that y with the sine of t. And you can see it right there. Sine of negative t is negative sine of t, therefore sine is odd. So this is kind of a hand-wavy, a little bit of a hand-wavy proof, but not terrible actually. This is pretty rigorous. So let's go ahead. I don't like how small that's written, so I'm going to write it slightly larger, sine of t. All right, so this tells us that sine is odd. Cosine of negative t being the cosine of t tells us the cosine is even. Tangent of negative t, well, that is actually the sine of that negative t over the cosine of that negative t, but we know that cosine is even, so that's going to be cosine of t, and we know that the sine is odd, so it's a negative sine of t, which is actually the negative tangent of t. So tangent of negative t is the negative tangent of t, implies tangent is odd. So this is the proof that the sine is odd, the tangent is odd, the cosine is even. So what do we say here? The sine, let me get the right color highlighter. The sine is odd, the tangent is odd, and the cosine is even. We've proved that so far. And now the reciprocal functions are proved the same style of, same way, except you would just use, actually it wouldn't be the same way, I'm saying it out loud. The cosecant of negative t is 1 over the sine of negative t. But sine is odd, so that's 1 over the negative sine of t, which is a negative 1 over the sine of t, which is a negative cosecant of t. There we go. So cosecant is odd. And the rest kind of flow, the secant and the cotangent flow the same way, but we've proven it for the cosecant, the sine, the tangent, the cosine. I'll leave it to you to prove it for the cotangent, that the cotangent is odd and the secant is even, but they flow the same way as how I've done the cosecant here and the tangent up above. So that shows us the odd and even identities. These are definitely memorizable. They're very, very, very powerful to use. Although in computation, you don't use them a lot. You do use them a lot when it comes to graphing. Now, if this is an algebra course, the first thing that you'd be asked after learning about odd and even functions is determine whether this function's even, odd, or neither. So we might as well just showcase that style of problem. As you know, just from years of algebra, that to determine whether a function's even or odd, you just start with f of negative x. Well, let's see, that's tangent of the sine of negative x. But we happen to know that sine is odd, so I'm going to say this is equal to the tangent of negative sine of x. And again, that's because sine is odd. And then we also know the tangent is odd. So if I was looking, for example, at the tangent, I should use a different color for this. The tangent of a negative number, it would be equal to the negative tangent of that number, because tangent's odd. So this is tangent of a negative something, sine, but doesn't really matter. So I could write that as the negative tangent of that something, which is the sine. Notice this is actually the opposite of the original function. So f of negative x ends up being negative f of x, implies f is odd. There you go. So that's how you would showcase that a function's even or odd. You know that, again, from years of algebra. So there's not a huge additional amount of confusion here. As I had mentioned in the previous video, as you move through trigonometry, you start learning several ways to do the same problems. And here is yet another way to do a problem. So we're asked to evaluate sine of negative 60 degrees, but we're asked to use the fact that sine is odd. So how would you do that? Well, because sine is odd, sine of negative 60 degrees is the same thing as negative sine of 60 degrees. And then I would just go for my 30, 60, 90 triangle. Here it is, 30, 60, and 90, 1, 2, root 3. And then the sine of 60 degrees, opposite over hypotenuse, root 3 over 2. So that's going to be a negative square root of 3 over 2. That is how you use an odd property to help you evaluate a trig function. If you were to not use an odd property, let's suppose that instead nobody told you what to do and they just said evaluate this, you could have easily done this problem by saying, well, I rotate down 60 degrees. And I went ahead and filled that in there. Notice that we are in quadrant 4. So as I've mentioned previously, that trig is pretty much about reference angles and quadrants. We are in quadrant 4. Our reference angle is 60 degrees. So if we were asked to find the sine of that negative 60 degrees, I would use the quadrant to let me know that, well, in quadrant 4, sine is negative. And then I would evaluate, instead of the sine of negative 60 degrees, I'd evaluate the sine of the reference angle. And 60 degrees, its sine is root 3 over 2. And so again, this just tends to be, or ends up being, negative root 3 over 2. Same answers. And if you're not told which one or which tactic to use, you could use either. It doesn't really matter. I tend to go back and forth with how I use odd and even identities to evaluate trig functions. I have a really not a bad habit, but I have a habit of just using like a triangle like this on a Cartesian coordinate system and using reference angles and quadrants. I like one method that always works rather than specialty methods. Okay, so as I've mentioned in the previous video, I want to sneak in proofs. And so here's another proof. If you are not familiar with proofs, you should watch the previous video because I stepped through kind of the ideas, how you would tackle this, a proof in trigonometry. Between these two sides, the more complicated side to me is the side with the addition or the subtraction. It's easier to glue an addition or subtraction together than it is to take a quotient and pull it apart into an addition or subtraction. So I would start with the left-hand side because, again, it looks more complicated to me. So I'll write down here the left-hand side and I'll copy it. That's equal to the secant of theta and then minus the cosine of a negative theta. And I have to make a decision. What do I do from here? Well, the very first thing I see is an even-odd identity. In other words, the cosine of a negative theta. We know that cosine is even. Just point an arrow at that and just say even, which means that the cosine of negative theta will turn into the cosine of theta. So I'll go ahead and write that down. This is going to equal the secant of theta minus, and I'll use blue just to showcase that this is the piece that just changed. And it's because it's an even function. Now, keep your eye on the prize. Where do we want to end up? We need to glue these two statements together to become a single fraction. That means we need a common denominator. Well, the fact that I just said the word denominator tells me I would like to write that secant as 1 over cosine. It just tells me that I'd like to get a denominator going on. So let me write that in blue. That's the one that's changing now. So 1 over the cosine of theta. And then I'll just put minus cosine over here. And you could see that we would be able to add these up if you multiplied the numerator and denominator of the second term by the cosine of theta. Then they would have a like denominator. So I'm going to go ahead and do that. I'll say this is equal to 1 over a cosine of theta, and then we multiplied numerator and denominator. of that second term, and it became a cosine squared of theta over a cosine of theta. Now that they have the same denominator, you can add them up, or in this case, take their difference. That'll be a 1 minus cosine squared of theta all over a cosine of theta. And again, always look at the prize where you want to end up. You want to get a sine squared of theta over a cosine of theta. Well, we have something over a cosine of theta, and that something actually is a sine squared. You just have to remember the Pythagorean identity, which is that cosine squared of an angle plus sine squared of the same angle is equal to 1. And if I go ahead and subtract cosine squared from both sides, you get this wonderful identity. Sine squared is 1 minus cosine squared. I see a 1 minus cosine squared down the lower left-hand side of the screen here, so I'll trade that out for a sine squared. So this is going to equal blue for the fact that I'm just changing that into an alternative form all over cosine. And that is the right-hand side of what we wanted to prove. We started with the left-hand side through a chain of equalities, also through deductive reasoning and theorems. We arrive at the right-hand side. This has been proven, QED. Now, I don't want to pan the even-odd identities. You do use them quite a bit, but there's not much else I can do with them in this video. So I'm going to finish this out with a gateway into the next major topic within most trigonometry courses, which is graphing. So what do the even and odd identities tell us about the graphs of the trig functions? Now remember, the following functions are odd: the sine and the tangent and their reciprocals. And we know that graphs of odd functions are symmetric about the origin. So all of these functions right here, if we know how to graph them, they're going to be symmetric about the origin, which is super helpful with graphing, because that means that if you have an infinite graph, or it's something that goes on forever on both sides, if you know your function's symmetric about an origin, then you only need to graph one half of it, and you can copy that half over to the other side by rotating about the origin. That's going to be very helpful as you move through mathematics. And then as far as the even functions, the only two are really the cosine and its reciprocal, the secant. This just means they're symmetric about the y-axis. And again, that leads to really quick ways to help us graph. Because again, if you have something that's symmetric about the y-axis, let's say you were given a function and they tell you, oh, your function kind of looks like this, okay? And they say, by the way, that is an even function. Well, now that I have half of it, I have the whole function then, because it's symmetric about the y-axis. It's just a mirror image about the y-axis. So that's very, very helpful when it comes to graphing. You really want symmetry with your functions if you can get it. But often it's not the case. But luckily with trig, all the functions have some type of symmetry to begin with. All right, this concludes all of the information you need for the fundamentals of trigonometry. From this point forward, you're going to go into graphing trig functions, solving trig equations, proving trig identities, and using something called the law of sines and law of cosines. So there's quite a bit more in trig to go through. But this is the foundation. You want to make sure everything that has been covered up to this point in this video series on trigonometry that you are awesome with. Otherwise, the rest of trig's going to be very shaky for you.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.